Hi, today I'll be talking about different bases, which will be the subject of the first ACSL short problem contest. So to begin, we need to talk about base 10. And this is the most commonly used base. It's the base used in daily life. But you may not have heard this term before because base 10 is so common that like people don't really think about it when they just use it because it's right. So say we have the number 3,514. And let's say this number is in base 10. Well, what does it mean for the number to be in base 10? Well, we can decompose this number as 3,000 plus 500 plus 10 plus 4. And you can see now that each of the digits is actually being multiplied by a certain power of 10. And you see in base 10, you can use any of the digits from 0 to 9. And here, 10 to the power of 0, remember that anything to the power of 0 will always be 1, right? So what it means to be in base 10 is that each place value represents a different power of 10. So this one represents 10 to the power of 3, 10 to the power of 2, 10, and 1, right? So you'll be multiplying the digit by that value of 10, and then you add them up to get your number. So with each new place value, you're multiplying by 10. So what does it mean when we have a different base, a base that's not base 10? Well, one of the most common bases that you'll have to use is base 2, which is also called binary. Also, I might have written it already, but base 10 is also called decimal. Yeah, you might need to know this because it might ask you to convert to decimal, and that just means to convert it to base 10. So base 2 can be called binary. And base 2 has digits, 0 and 1, and it doesn't have any other digits. So the numbers in base 2 only have 0 and 1. And computers will use binary to process code. So let's see an example. When we have the number 1011 in base 2, what happens when we want to convert to base 10? And having a subscript of 2 means that it's in base 2. So how do we convert it? Well, given what we know about how base 10 works, we can see that each place will represent a different value, right? So this place will represent 1, this will represent 2, this will represent 4, and this will represent 8, because these are the different powers of 2. So now to find the total number, we know that it will be equal to 8 times 1 plus 4 times 0 plus 2 times 1 plus 1 times 1, which is equal to 11 in base 10. You can write base 10, subscript 10 if you want to indicate explicitly that it's in base 10. This is a basic example of how to convert from base 2 to base 10. But what if you want to convert a base 10 number into binary? Let's say we have the number 83. How to convert this into binary? Well, one way to do this is to think about how many of each power of 2 can go into 83. So think about what's the biggest power of 2 that can go into 83? That's 64. And then what's the next biggest power of 2 that can go into 83? Well, after you take 64 out of 83, you have 19 left. So then it'd be 16. And then together this is 80. So there's only 3 left, which is 2 plus 1. Now we have written 83 as the sum of powers of 2. So this lets us know that 83 would be equal to 1, 0, 1, 0, 0, 1, 1 in base 2. Think about why this works, because this will represent 1, 2, 4, 8, 16, 32, and 64. So the digits, the numbers that you have in your sum will be the ones that have ones, which mean that they appear in your number. So that's a basic summary of how to use base 2. Now let's think about another base, base 8. This base is also sometimes called octal, because octal is I think it's the Latin root for 8. And this will have digits from 0 to 8. I mean 0 to 7, sorry, 0 to 7. So for example, if you have a base 8 number, for example, 3, 1, 7, base 8. If you want to convert it into base 10, you would do 3 times 8 to the power of 2 plus 1 times 8 plus 7, which is equal to 3 times 64 plus 8 plus 7. And if we calculate this out, this would be equal to 207, I think. This is 180 plus 12 is 192 plus 8 is, 207. Okay. So this is how to convert from octal into decimal. But what if you want to convert from base 10 into base 8? Well, say you have like 422, base 10, and you want to convert to base 8. Well, it's actually a bit harder than converting from base 2. Because if you want to convert into base 2, at most you have 1 of each power of 2, right? But if you want to convert into a different base, such as base 8, then you might have multiple instances of that power of 8, which would make it trickier. So here, you can utilize a trick. You can also use this for base 2 or for like any base to convert it from base 10 into that base. So first, you take 422 and you divide it by 8. This will be 52 with remainder of 6. And then you take 52 and you divide it by 8, and this will be 6 with a remainder 4. And then lastly, you have 6 divided by 8, which is just 0 with the remainder of 6. So what do you do with all these like remainders? Well, you go from back to front. So you look at the last remainders, and it will give you the answer of 646 base 8. And we can verify this by converting this to base 10 again to verify our answer, right? It's equal to 6 times 64 plus 32 plus 6 equals to 360, 384, 422. So then you have verified your answer. So summarize trick is you continuously divide your number by the base you want to convert it into, which will give you a number and a quotient and a remainder. So you take the quotient and you keep dividing it until your quotient is 0, and then you look at all the remainders and you go from back to front and write a number, and that will be your final answer. Okay, finally, we have to talk about another base, which will also be covered in the contest, which is base 16. This base is called hexadecimal, hexa 16, hexadecimal. Now hex is 6, decimal is 10, so together it's 16. And sometimes it's just called hex. And this base is a bit special because 16 is greater than 10, right? In effect, base 16 will use more digits than base 10. So it'll use all the digits from 0 to 9, but it'll also use the digits A, B, C, D, E, 10, 11, 12, and F, 13, 14, and 15. So what these digits essentially represent are 10, 11, 12, 13, 14, and 15, but represent them in like shorthand, or not in shorthand, but they represent in one place value. So when we convert from base 16 into base 10, let's say we have the number A 4 F, base 16. Well, we know that A is actually equal to 10, and F is actually equal to 15. And this will equal to 16 squared is 256. This is equal to 2639 base 10. And when you want to convert from base 10 to base 16, you can use the same method of division. So say we have the number 257 and we want to convert it to base 16. Actually, this is pretty easy because you know that 257 is one more than 256, which is a power of 16. But let's try to use the division trick and see what we get. So 257 divided by 16 is 16 remainder 1. And then 16 divided by 16 is 1 remainder 0. And then 1 divided by 16 is 0 remainder 1. So again, we take the remainders from left to right, which will give us the answer of remainders 101 base 16, and that will be equal to 257 base 10. Also be careful to make it so that it's obvious you're writing a subscript like that. Okay. So now, have you noticed that 8 and 16 are both powers of 2, right? And this means that there's actually shortcuts if you want to convert from base 2 to base 8 or base 2 to base 16. And vice versa. So first, how do you convert from base 2 to base 6 to base 8? So say you have a base 2 number 100011010. And this will be pretty tricky if you want to convert it to base 10, then convert it to base 8, right? So how do you convert it directly from base 2 to base 8? So here's the trick. Because 8 is equal to 2 to the power of 3, so we want to look at this number in groups of 3. So when we take these, so let's convert each of the numbers in the brackets into base 10. This will be 2, this will be 3, and this will be 4. Note that the number in like the brackets will always be less than 8 because the biggest 3-digit number you can make in base 2 is actually equal to 7. So you never have to worry about like it can't be a digit of base 8 because it's too big. So now that you've converted this into like 4, 3, and 2, it's actually pretty simple. You can just know that it's 4, 3, 2 base 8. Even if it's not like all the digits can be grouped up. For example, like 1011 base 2, you want to convert it to base 8. Well, you can group these two digits up to be 3, but this digit you can't group it up. But it's fine, you can just leave it like that, and it will be 13 base 8. And if you want to convert from base 16 or base 2 to base 16, then it's a very similar thought process. You know that 16 is equal to 2 to the power of 4. So for example, if we have the number 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, base 2, and we wanted to convert it in base 4, we take each number or each string of digits in groups of 4. So if we convert this into base 10, this would be 8, this would be 13, and this would be 6. So we know that 13 is equal to, I think it's C. D, never mind. 13 is equal to D. So our base 16 number would be 8D6. What if you wanted to go the other way? Octal to binary. Or hex to binary. So to go from octal to binary, say we have the octal number 7, 3, 4. How do we go from this into binary? Well, it's pretty simple. You just take each digit and you convert it into a base 2 number. So for example, 7 is 1, 1, 1. And then 3 is 0, 1, 1. And 4 is 1, 0, 0. So that's what it is. Hexadecimal to binary is the same principle. If you have, for example, C to 0. C is equal to 12, right? A is 10, B is 11. So C is 12. And 12 would be 1, 1, 0, 0. 2 would just be 0, 0, 1, 0. Since you have to make sure to include the correct number of zeros in the front. For example, we know that 2 base 10 is just equal to 1, 0 base 2, right? But we still have to include these extra zeros in the front as like placeholders because we're converting from base 16, so the numbers still have to be in blocks of 10. I mean blocks of 4, sorry. Blocks of 4 like this to represent each digit. And of course, 0 is just 0, 0, 0, 0. Okay, now let's look at some of the examples that ACSL has. Wait, actually, I spoke too soon. There's 2 more topics that I still have to briefly mention. First is octal to hexadecimal. This one is, there's no like simple way to do, well, there's no shortcut. You just first go from octal to binary, then go from binary to hexadecimal. So you can't go directly from octal to hexadecimal. You just have to go to binary in the middle. But it's still a pretty quick process. One more topic that we have to talk about is operations. In other bases. So in base 10, let's think about what happens in base 10 if we want to add, for example, 1, 2, 9 and 4, 7, 3. So we know that 9 plus 3 is equal to 12. So that means we have to put a 2 here and carry the 1. Why is that? It's because 12 is equal to 10 plus 2. So because 10 is a higher place in place value, we have to put it in like the correct place, the tens place, right? You don't think about it a lot when you do base 10 arithmetic, but you need to pay attention to it when in other bases. because other bases will also use like their other base as like the standard. For like when you need to carry a number. So for example, if we have 101 base 2 plus 011 base 2. Well, we know 1 plus 1 is 2, but 2 is equal to 10 base 2. So what we actually want to do here is we put a 0 and then we carry a 1. And then we have 1 plus 1, which is 2 again. And then we carry another 1. So in the end, you would get 1000 base 2. Same principle for base 8 and base 16. Let's say we want to multiply two numbers in base 8. You have like 4, 1 base 8, like 6, 3 base 8. And you want to multiply these numbers. Well, first you have 1 times 3, that's 3. And then you have 4 times 3, and that's 12. But 12 is equal to 14 base 8. So instead of actually putting 12, you would put 4, 1 to keep everything in base 8. And then 1 times 6 is 6. 4 times 6 is 24, but that would be equal to 30 base 8. So this is what you would have. And then when you add it, you still have to pay attention to like stuff being in base 8. So here you have a 3, and then 4, 6. 4, 6 is 10, but 10 is 8 plus 2, so it'd be 1, 2 base 8. So what you put here is a 2, and then you carry a 1. So the answer would be 3, 2, 2, 3 in base 8. Let's do another example with hexadecimal and subtraction. I don't think it'll ever ask you to do division between like in a different base. So I don't think you need to worry about that. So let's say we have the number 3, 2, 1, and we want to subtract A4. Well, obviously 1 is smaller than 4, right? So we need to carry a value. So when we can reduce this 2 to a 1. But the number that we're actually adding to the 1 would be 16. So instead of becoming 11, this after taking like I forgot what they call that in elementary school. Well, after exchanging the value, it will become 17 because it will be 1 plus 16. Because we're in hexadecimal right now. So then you actually have 17 minus 4, which is 13, which is D. And then you have 1 minus A, and again, that's not possible. So you do 2, and then this again, it becomes 17. So then 17 minus A is 10, so that's 7. So the answer is 270. Okay, now I think we can look at the examples from ACSL. Okay, here is a problem. What is the value of 111011 in base 16? Well, first let's write this number down. 1110 100 1011. And we want to convert it to base 16. So remember what we have to do is to group the digits in clumps of 4 and convert it. So 1011 is 11, which is equal to B. 100 is 4, and 111 is 7. Yeah. So the answer would be 7 for B. And checking the answer given by ACSL, that's correct. Now we have the problem. What is the value of 1 ACE 16 plus 4, 5, 6, 16 in hexadecimal? Well, E is equal to 14. Yeah, E is 14. And 14 plus 6 is 20. And that's 16 plus 4. 16, what am I doing? 16 plus 4. So then you have 1 plus c plus 5. C is equal to 12. So 1 plus c plus 5 would be equal to 18, which is 16 plus 2. And then you have 1 plus a plus 4, which is 15, which is f. So the answer is 1f 2, 4. And that is correct. Next problem. So this problem says, what is the value of 135 in base 8 in base 10? Well, this is pretty simple. Using the definition of a base, we know this place value represents 1, this represents 8, and this represents 64. So it'd be 64 plus 3 times 8 plus 5, which is 29 plus 64, which is 93, which is correct. Next problem asks about hexadecimal number, and it says on the RGB color table. It's not super important what the RGB color table is, but just so you know, RGB color table is a way of representing colors as a hexadecimal number, where every like 2 represents like the value of the amount of red and the amount of green and the amount of blue in the color. It's not very important and you don't need to know that, but it's a fun fact, I guess. So it wants you to convert 38B0DE into decimal. Into decimal. But actually, rereading the problem, it only wants the blue component. So I guess what I said earlier does matter. Okay, so 38, B0, and DE. As I said earlier, these represent R, G, and B. And since what it wants is the value for the blue component, you only need to care about the last 2 digits, which represent the blue component, which is DE. So you want to convert DE into base 10, which D is 13, and then E is 14. And 13 times 16 is, I'm hesitant to say that. 873. Yeah, I was wrong. It's 208 plus 14 equals 222, base 10. And correct. Okay, next problem asks for the average of 3 numbers when you convert it into base 10. So we need to convert each number into base 10. This is equal to, well, this is 2, 4, 8, 16. So this is 16 plus 3. This is 19 base 10. This is equal to 17. And then 1e is equal to 31. So you want to find the average of these 3 numbers. You can find the average by adding the numbers together and dividing by the number of numbers. And that's the definition of like an average. So 36 plus 31. Let me check this. I might have done it. Oh yeah, I messed up. So this actually always trips me up. E is 14, not 15. So this would be 30. My bad. So then the average would be 22. And I checked, and this is correct. I think that's all of the problems. Yeah. So I found these problems on acsl.org slash get started slash divisions slash intro to element. And this is where you can find study materials if you want to review this content again.